And this compact notation has that much of things going on inside. Okay, there's a word calculation of two vector fields that are 90-degree apart from each other with the same magnitude. Okay, and another thing is that if you this is the very definition level, if there's a simply connected region, and we have, let's see if I use simply connected region, subregion inside a D again, then what happens if I parameterize along this one at DZ? If F is analytic on A, if analytic on R, if we have that condition, what happens if you go around this boundary of a simply connected region D inside the simply connected region R? What happened to that? It's supposed to be 0, and in the homework I asked you to prove this one is a 0. How was that? Are you able to prove that? Nope. So here is FCDZ. By definition, these are the definition, right? These are the definition. And here is gamma u dx minus v dy plus I times gamma v dx plus u dy. And then in backward, I did it in class, and it was, I hope you recognize that part. This is not gamma. What is the right notation instead of gamma? The curve here is boundary of D oriented positively for the region D. That's this notation D means, right? So what theorem do we use to conclude this one to 0? Passing to double integral. What theorem is that? From line integral to double integral? What theorem in the plane? Green's theorem. 1 or 2 here. It's a simply connected region. It's 1, right? So it's 1, and what does that become? D, the region itself, right? Then what is this one in here? Curl, right? So can we calculate the curl? This one goes to front, differentiated with respect to x. You cross it, minus this one goes in a uy, right? That was the curl, remember? And dA. Plus, second one has I multiplied there, is this number. And this one again. What is the curl here this time? ux, right? Minus vy dA. Okay? So I didn't use anything except that it is just defined and differentiable. Why is this guy 0? Yeah, why is the curl 0? Integrand is 0, absolutely. Therefore, this 0 plus I is 0. Why is this guy 0? This is where CRE kicks in. Already mentioned that, right? It's analytic CRE makes these things 0. What I did in class on Thursday is that I started with the CRE. I did all this one backwards. That's what I was doing in class. Okay? All right. So here's a theorem. Important theorem. For a simply connected region, if you go around the simple close the curve, the complex integral is going to be 0, right? So let me state that. This is called Cauchy theorem. Cauchy's theorem. Just going to use a picture. Here is curve C, positively oriented for the inside region and no singularity. You know what that means, right? No singularity in there. And if F is analytic, inside there, then on that region, then what happened to the integral of c of f c dz? It becomes 0. That's called Cauchy's theorem. Now, how would you recap in 2 sentences why this one is a 0 after going through all that? First, where is the simply connected region inside? Well, it's a simply connected region because we filled in, and the key thing is that it has no singularity in there. Okay, that's the key thing. So how do you use this no singularity in there? In going to the 0 in there. That's what the Green's theorem requires inside, right? Has to be all defined. And why is that 0 then? That's how this one is how that no singularity used to satisfy, to use that Green's theorem. And why does it become 0? Because the curl of each thing, because the CRE became 0. That's kind of one way to summarize this one. Make sense? Does that make sense? All right. Let's pass to next version, Cauchy-Goursat Theorem. The second guy realized that we actually have a better statement than that. So it goes like this. If you have a region, and now we have singularity here and there and there. Our function f of f is not analytic there. Okay? Is analytic with the singularities in there. Within the enclosed region. You see the different situation? We have a curve within that enclosed region, we have singularities in there. Before, we have no singularity within the enclosed region, correct? So the situation in here is that we have a curve outside C. I'm going to call that C0. And if you put any curve around it, C1, also around that singularity, it's kind of positively oriented, right? Around that singularity, not necessarily a circle, anything, positively oriented, C2 and C3. And you can imagine there are many more, but finitely many more, okay? Isolated singularity has to be finitely many more. Then what happened to this integral around dz? Not 0, right? Anybody remember what happened to the Green's theorem applied to this type of thing? Sum of this individual thing in there. K going from 1 through n. If there's 100 of them, you have to do it separately. Going around all of the 100 singularities is the same as individually go around the singularity, avoiding each other, and add them all up. Okay? So I hope this is clear from the Green's theorem too. Okay? And there should be no more singularity outside this region, and that's where actually how it's used. Okay? So that's called the Cauchy-Goursat theorem, and I hope after going through that much of discussion in Green's theorem too, if this makes sense. This is actually how you use it. All right? All right, see if I have good examples here. All right, here's one example I have. Example. Going around C is 1 over z minus I dz. All right, what is this? So if I'm going to give you the several pictures, and here's xy complex plane. The I is in there, so I's. You know why I'm pointing out I in there? What is the name of this fancy name of this I for that function? F of z, 1 over z minus I. This I is the blank of the function f of z. What is that word? Singularity. It's not defined in there. What kind of singularity is that? There are like 6 kinds of singularity, right? What kind of singularity is that? Pole? Remember, if it's appear nicely in the denominator, it's a pole. Pole of what order? Order 1 is called simple order pole. Okay. All right. So I'm going to sketch several versions of C. All right. So what if I go around C like that? All right. That's my C. And what is the integral over the C here? What do you think? We're going to use Cauchy-Goursat theorem because the area enclosed by C has no singularity in there, right? So you can nicely avoid that I and apply Green's theorem 1. So that answer here is 0, right? All right, let's do the second one. How about doing it like this? Easy one, and that's my C. Then that's the red one, C2. Let's say going around C2, FZ, TZ is not going to be 0, right? It's not going to be 0. But you can always choose this whatever C3, FZ, TZ. So what's this C3 is going to be, you think? C2 is some arbitrary in here, some possibly wobbly curve. Then what is C3? Anything, that's the theorem, but in practice, what is the C3 is going to be? Small circle around that I, right? So let's see who can parameterize this one nicely using complex numbers. Radius r goes like this, right? And going around, you put e to the it. If r is small, and then you can avoid whatever that C2 is out there, making r whatever the small, it eventually cancels out, turn out. But it's not quite the circle around I. The circle around the origin, right? Understand? Circle around the origin. So how do you make this one circle around the I? You multiply I in there. Not multiply, add I in there. Another way to look at it here is that you take that denominator z minus I, you want to make that one circular. And then if you solve for z, then you have I plus r times e to the it. Knowing that, what happened to 1 over z. And so this is not really a trick, and it's just a little comparison. So if you do that, this calculation, C2 could be possibly more subtle and complicated, and is equal to C3, the small one. So let me actually complete this problem. So here's y, here's x, and here's I. Let's see if this is my C2. Going around like this, that's my C2. And my C3 is a small circle around there, C3. So compute C2, that's my integral symbol. Some suspicious file, what does that mean? 1 over z minus I dz. What's going on there? Is what we're calculating. But how do you actually calculate this? C, same as which one? C3, which is a small circle there. That's Green's theorem 2, consequence of Green's theorem 2. The z minus I dz. Make sense? And C3 is that parameterization, this colon, z equals r times e to the it plus I, where r is some small constant and t is the only variable. Any questions so far? Replace that loop with a simpler loop, doing that same thing we did for f and g all together in terms of complex. All right, so therefore that C3 integral is going from where to where? T value from where to where? 0 to 2 pi. And what's going to happen in the denominator if you replace that z with this one? R times e to the it. You see that? I cancels. And z minus I becomes r times e to the it, right? Then you have to multiply dz dt. Here is the z prime, correct. And z, here's that. So it's r times, what is the derivative of this one? I times e to the it. What about derivative of I? Plus 0, constant, right? And that becomes dt. All right? Then is that I cancels and r cancel, I doesn't cancel, and here's 0 to 2 pi of just a real number as a 2 pi I. So this is something we practiced last time, but it's coming from slightly different context. Sure, we don't have any question about this one? Everything good? All right, let's try this one. There's this curve C, and we're integrating sine z dz. And C is this curve from 1 plus I to 2 plus 3i, and it is connected by some curve which is satisfying this Cartesian equation. So here is x, z equals x plus iy. All right? I can even write down Cartesian equation. Does it look like Cartesian equation? What do I mean by Cartesian equation? Then is it more complicated? Y squared and x and y multiply, things like this. Something that is difficult for you to isolate y, but it is nicely isolated here. So what would be the parameterization of this one? It's going starting from here. This is initial complex number, and that's the terminal complex number. So I have to give the orientation. Starts there and ending it there. Can you parameterize this one? There is your x being t and y whatever this one. This is your parameterization nicely. But if it is like this, it's harder to parameterize. Would you agree? It's harder to parameterize with respect to t. But here is that y is isolated, so it's easier to parameterize it. So you can parameterize it and stick it in there and go through that definition of a sine z and all that, right? So it looks like a complicated calculation. So see what this Cauchy's theorem it's really implying. How about this one? Is this analytic? Does it have a singularity? Let's think about the definition again. What is sine z? If I remember the definition. So that's the problem. Any conceptual question about what the problem is asking? We anticipated that it's hard calculation, so try to do some trick. Anybody remember the definition of a sine z? It was like hyperbolic. It's just like hyperbolic sine and hyperbolic cosine hyperbolic. Those things, right? E to the iz, right? Iz, and plus or minus e to the negative iz. What's in the denominator? It was a 2i, I think. Oh, the 2i. That's the definition. Okay? So it goes like that. So here's one way to look at it. So the reason I looked at this definition is that analytic or not. Right? Analytic on, does it have a singularity? E to the I is defined everywhere? E to the I is defined everywhere, remember? If it has log, it usually has singularity. Something has a denominator, has a singularity. So it's analytic on what space? Analytic on the entire C, right? Entire C. So Cauchy's theorem and Cauchy-Goursat theorem. Cauchy's theorem. There's no singularity whatever curve you put, right? So it's going to be 0 all the time. If you start and come back, it's going to be 0. So think about how we use that to calculate this one. Anybody remember that this type of condition is called some independence? Anybody remember that? That's one thing. There was another thing, another independence. What was that? Path independence. Path independence is equivalent to that. I claim that when I introduce path independence. Okay? It's because going like this is the same as going like that. That's the meaning of a path independence, right? So you go around like this, and going backward is going to be 0. That's what it says. So if you break these two apart, it gives you the statement you want. That's a path independence. So because of that, we have path independence. And then you use that meaning of a path independence. You can get to the beginning and end point however you want, not following through these complex cubic polynomials, right? Correct? Yeah. So choose any path. That's starting 1 plus I to getting to 2 plus 3I. You look at that function and decide whether this making the circle is going to be nice, or straight line is going to be nice, or making this derivative vanishing like that is going to be nice. Whatever, something that is making the calculus the best as possible, right? So I'm going to call that one gamma 1, gamma 2. You don't have to follow through that whatever they suggested. You can go whatever you want, however you want, and the answer is going to be the same. That's the path independence, right? Good. So let's parameterize gamma 1. So let me first write down the outline. So what is the original name of this curve? C. So that will be different curve. I'm going to call that one E. It means for any E, right? For all E, for all E. That makes this path independent. So, of course, for C as well. So the original problem, the integral from C is equal to gamma 1 plus gamma 2. Does that make sense? Going through that complicated C is not necessary. Go through anything that's convenient. Go through gamma 1 first and along the gamma 2. As long as you start and end at the same, path independence will give you the same value. Okay? So how would you parameterize gamma 1? Z is, as you go along this gamma 1, y coordinate is always the same. There's this y coordinate I there, right? How about x coordinate? Maybe you can just write as a t, and t varies from where to where. 1 to 2, is that right? Yeah, 1 to 2. Okay. How about gamma 2? Gamma 2 is here. X coordinate is always a 2, right? Here's a 2, correct? And what about the other one? It's a ti maybe, and t varies from where to where? 1, 2, 3. Is that right? 1, 2, 3. Is the orientation correct? If it is actually going backwards, and you may have to use negative t as t going from 1 to 2 if it actually going to the backwards. You have to make sure you actually get the orientation correct with it along with the t. So the integral along the C is the same as gamma 1. Gamma 1 going from 1 to 2, right? And sine of z is a t plus I, correct? And multiplied by dz dt. What is dz dt here? It's just a 1. dz dt is t equals 1. So that part's pretty nice. All you have to do is stick in this one into complex definition and integrate along the t. It's not bad at all. It's really pretty neat calculation. So what about the second part? Going through 1 through 3, right? And what about this one here? Sine of 2 plus ti multiplied by dz dt here. This time it's just I. Is that right? Yeah, it's just I. So I is multiplied out there, dt. I, you can pull it out, and going through the complex definition of integral, it's really simple. Okay, let's do that. It's not really just saying it's really simple. Let's do this. 1 over 2i is out there, and e to the iz. So if you multiply I there, it's a negative 1 plus it there, right? Minus, this one is negated, it's 1 minus it, and dt. That's the first one. Okay? Second one, 3, and 1 over 2i again. And e to the, this one multiplied by I is a 2i, so it's going to be negative t plus 2i minus t minus 2i, because negated. But there is a I outside there, so make sure you don't lose that. Things like that. So, well, at this stage, I want you to just try that. Okay, that part is going to be e to the negative 1 times cosine t plus I sine t. Remember that thing? Okay, so you integrate cosine t and sine. That's not bad, right? Yeah. So go along like this. I think that kind of answers how the rest of the part goes. Make sense? That was the application of which theorem? Cauchy or Cauchy-Goursat theorem? The whole thing is just the Cauchy-Goursat, right? Cauchy, not Cauchy-Goursat. Cauchy-Goursat is just a matter of rewriting it. It's not really convenient. It's a matter of rewriting the integral into the several part. If there is really singularity, you actually have to integrate along some simpler curve, right? Like a circle or rectangle, if that makes the integral easier, things like that. Make sense? All right, we're going to practice more of this type of calculation.